Suppose we're given f of x comma y, and the region R is a rectangular region shown here below in the xy coordinate plane. We're asked to evaluate the given double integral. Let's first define the region of integration in terms of x and y. The interval for x would be the closed interval from 1 to 3. The interval for y would be the closed interval from 2 to 5. These two intervals give us the given rectangular region of integration shown here on the coordinate plane. Next, notice how f of x comma y, which is equal to x divided by y, would be non-negative over this region, which means this double integral is equal to the volume of the solid bounded by the function in the xy plane over this region. Let's look at this graphically. This graph is pretty busy, and we'll look at the second graph in just a moment. But the blue surface is the graph of f of x comma y. The region of integration is this rectangular region here bounded by these four planes. And notice how the function is non-negative over this region, which once again means a double integral is going to give us the volume below the surface and above the xy plane over this region. If we zoom in on the region of integration, we get a much better graph. So again, here's the surface graphed in blue, and now we're looking only at the region of integration in the xy plane. If you look down the xy plane, here, this is the region of integration. So our double integral is giving us the volume of the solid bounded by this surface and the xy plane over this region. So going back to our work, let's rewrite this with the limits of integration for x and y. So we'd have the double integral of our function x divided by y. Notice how we integrate first with respect to x, then with respect to y. So the limits of integration for x are going to be, again, from 1 to 3. And then for y, the limits of integration will be from 2 to 5. So we first integrate with respect to x, treating y as a constant. The integral of x with respect to x would be x squared divided by 2. So we'd have x squared divided by 2y. We need to evaluate this at the limits of integration. These limits of integration are for x, so we substitute these values for x, not y. So this will give us the integral from 2 to 5 of, when x is 3, we'd have 3 squared divided by 2y minus, when x is 1, we have 1 squared divided by 2y. So notice how we have 9 over 2y minus 1 over 2y, which is equal to 8 over 2y. So the integral from 2 to 5 of 8 over 2y. But notice how this simplifies to 4 over y. We could factor out the 4, but let's leave it as 4 over y. The integral of 1 over y with respect to y would be natural log absolute value y. But notice how the y values are already positive, and therefore the antiderivative is going to be 4 natural log y. So we'd have 4 times the quantity natural log 5 minus natural log 2. Notice here, because we have a difference of two logs with the same base, we can combine these two logs by dividing the numbers 5 and 2. So the exact value of the double integral would be 4 natural log 5 halves. Let's also get a decimal approximation though. So using the calculator, we'd have 4 natural log 5 divided by 2, close parenthesis, enter. To 4 decimal places, we'd have approximately 3.6652. So we found the exact and approximate value of this double integral, which in this case, again, because the function is non-negative over this region, it does represent the volume bounded by the surface and the xy plane over this region. So going back to our graph one more time, we just found the volume of this solid in here, again bounded by the surface and the xy plane. I hope you found this helpful.